might run a little long. This one might be just a little bit longer than what we did in the introduction last time, but it's going to vary. A lot of times it will depend primarily on questions that you may have. Is there something that we missed with regards to the overhead? Just in case, this is MEG 402, 645. If you're in the wrong course, now is the time to find the right one. You can still survive after the first week, but after that it gets you up top. By the way, how many are not mechanical engineering oriented? Okay, is there a civil engineer or is there an electrical or whatever? Okay, because the reason I ask is that some of the problems I will be slanting then more towards mechanical engineering and not every once in a while say a civil problem or something else. Okay, as I mentioned before, if you haven't gotten the book, it's the 5th edition by Chapra and Canale, and it's Numerical Methods for Engineers. I think you'll find it's a very good book. Somewhat expensive at times. By the way, I just discovered something in a newsletter that's called Bottom Line, and if you go to a website that has to do with India books, I can't remember exactly what it is. I'll look it up Tuesday and tell you, but you can get books at significantly reduced prices, any textbook. You just go to the website and then you can order it. That way, I just found out about it. Don't tell the book publishers here. Okay, let's do a kind of a quick review as to problems. You've been down this road before, and that's why we teach you to think like engineers in your introductory courses, statics, dynamics, things of that sort, as how to address a problem and then resolve it and solve it. Read the problem thoroughly, by all means. Truly understand what it is that the problem is asking. Then, you've seen this before, free body diagrams. Is there anyone in here who can't do a free body diagram? Okay, good, because I'd be somewhat suspicious as to how you got this far if you couldn't do that. All right, so what do you do with a free body diagram? You include all the forces and motion. If there's motion, if it's static equilibrium, obviously the forces are in balance. If it's not, it's moving. Establish the governing relations. Right? These are the equations. It's from these governing relations that you then will write or determine the recursion relation, a numerical technique that you will use to then solve those equations. Obviously, review the best possible numerical scheme for solving those problems, right, or those passive problems, and then ultimately write a code, examine the results. See what you get. All right, there's a nice example. I think it's in this textbook. I can't recall, but it has to do with free-falling bungee jumper. How many's done bungee jumping? Okay, so what did you tell us about it? What did you experience? You survived, I noticed.
Pretty bad until the bungee pulled me back up, and then it just jumped around like a ragdoll for a while.
Okay, so you bounced up and down. How far up was the drop?
170 feet.
How about you?
I don't remember how far it was. I just remember pain, like breaking the shins.
Okay.
Hurt like hell.
You didn't feel like your legs were being pulled out?
No, it felt fine.
You trusted the cord, obviously. Okay. Well, look, there are two things with regards to bungee jumping. Right? One is the downward force due to what? Gravity. And the other is the upward force due to air resistance. All right, so those are your two forces acting on a bungee jumper. Okay, so you begin with the free body diagram. So you sketch this out. You say, gee, I need to balance the forces on this. Okay? The two forces, gravity, air resistance. Kind of like common sense. All right, now, you're going to say, I got to come up with the governing equation. If I can't find it, then I got to derive it. When in doubt, particularly in engineering, you can almost always begin any problem solution with F equal ma. All right? So F equal ma. A is acceleration. Acceleration is the change of velocity with respect to time, so dv dt. All right, so I then can rearrange this as dv dt is equal to the force divided by the mass. Now the force consists of these two forces, right? gravity, and then also the air resistance. Now, I know what this is going to be as far as the drag, all right, or as far as gravity. So with this, I can say, well, it's mg, all right, so force is equal to mg, mass times acceleration of gravity. All right, so for the upward part, that would be the air resistance. That's minus CD v squared. Now I can pull this out of my little aerodynamics reference textbook or whatever. That's the coefficient for drag. And I can look that up for whatever the body would be. If it's really streamlined, it's going to be relatively small. If it's like a block of wood or a car or whatever, it's going to be pretty big. All right, so those are my two forces. I can plug those into this relationship, and what I wind up with then, dV dt is equal to g minus c sub v over m v squared. So I know that this relation is a function in v squared. All right? So v is the vertical velocity. We'll got to keep consistent units on this, so we'll use MKS, which is meters. Then t is time, gravitational acceleration, drag coefficient, and the jumper's mass in kilograms. All right? How many of you can do this problem if it were given in English units? Oh, yeah.
Old-fashioned.
The old-fashioned one. When you go out to the real world, as they say, you'll probably do things in English units. Your boss will look at you like, well, you don't do that stuff. What's MKS? Right? Okay. Two ways to solve the problem for velocity at various times. All right. The first way, of course, is analytically. When you have a very simple relation, you can say, well, I can come up with an exact solution to this. Nothing beats exact solution. So you can do that analytically. Right? If you can't do it analytically, then your only recourse is to do it numerically. So you're going to approximate the solution. You're going to let the computer beat this thing up and do it a number of times until it looks like you got the right answer. All right, so based on that equation, I know what the analytical solution is, and so I can jot that down. Here it's the tangent h, which is, here's the definition in terms of x. X would be a distance displacement. So then I can get the velocity here based on my tangent. I can also do this numerically. All right, so here I'm going to use a method called Euler's method. So what I'm doing is marching this solution. I want to know what the velocity is going to be over time. So here is v, t is n plus, notice the n plus 1. That means an unknown value. So time at an unknown value, the next step. T at n would be a previous value. All right, so I know what that was. And maybe I start with 0. Here is delta t. So what I've done is take dv dt. So here's the difference in v, here's the difference in t. Here's that right-hand side equation, all right? Now, what this means in parentheses is that it's a function of time. Okay? So I can rearrange this equation so that I say the velocity at the new time is equal to the velocity at the old time plus all this stuff on the right-hand side. Okay, so here's that delta t setting right in there. So I now have what's called a recursion relation. And it's based on that governing equation that we saw before. Okay, now I can also plot this out. So if I run the solution, I can say, okay, this is what I get for the analytical solution. Okay, so obviously velocity increases with time. It's going to asymptotically approach what? A terminal velocity. I think we all know that in some form, in some instances, when you're falling or an object is falling in the atmosphere, at some point it reaches a set value or a terminal velocity. And that's because there's enough drag resistance balanced with what the gravity is pulling on the object that says, okay, this is how fast I'm falling. I don't go any faster than that.
I'm sorry, sir. I didn't see how you went from the dv dt equals g minus cdm v squared to the one with the square roots. I thought you just moved over. Yeah, I didn't understand how you got to the top one, sir.
Right here?
Yes, sir.
That's an analytical solution. Okay? That means you can go to your math book and you can say, based on that ODE, that ordinary differential equation that I have, I need to solve that analytically or exactly. So if I do so, that's the analytical solution that I get. Okay, if you haven't done that, you probably did it in math in one form or another. If you haven't done it, it's a nice little exercise to do. So you've got a first order ODE, so you can actually solve that. okay? Now, whenever you have an analytical solution or an exact solution and you need to verify or confirm that your numerical solution, how good is it? What you do is compare it to the analytical solution. All right? So that way you can test the model, and then you can actually use the model later when you're actually doing a forecast where you don't have an analytical solution or exact solution. Okay, so this is what actually happens with the bungee jump. All right? So now if I do the approximation, the numerical scheme that I was just describing to you, what I've got here is that I want to approximate that first derivative of v with respect to t. Remember, that was a delta v over delta t. Right? So here's the delta v. Right? There's the delta t. All right? So this is what I would get with the analytical solution. Right? But what I've done is approximate this between 2 points. All right? What happens when I do that between 2 points?
It's a short distance.
Yeah, I have a linear approximation. All right? So I have a straight line. Get the idea? So what I've done is that I've already factored in here an error because I know that I'm not accounting for the curvature. I'm approximating this as a straight line on this. Now, if I do this enough times, what happens is that I shrink that distance down to where it becomes almost as close to exact as I can get. Right? So that's what we're doing. By the way, if I wanted to account for curvature, what's the next level equation that I would have to use?
Taylor?
Say again?
The Taylor?
No. Quadratic. Sure. What's the minimum level equation that allows you to handle curvature? Quadratic. Right? So a linear equation is going to be straight line. Right? Quadratic, curvature. What's the next level? Cubic. What does cubic allow you to do? Inflection. What an inflection is? An inflection. Like that. Right? So you can have curvature, more than one curvature. Curvature one way, curvature another way. That's what a cubic will do for you. Okay, let's compare the solution here with the analytical for the bungee jumper. So you see, here's the exact solution. All right, here's what happens when we run the numerical solution. And so it's tracking the same as the analytical solution, as you can see. Now we have error, we know that because of the grossness in the approximation that we use, the coarse intervals. If I wanted this to come as close as I could to the analytical solution, what would I have to do?
Run more iterations.
Decrease.
See these spaces? What happens when I start shrinking down the space, the intervals?
It's closer and closer.
Yeah, it gets closer and closer, right? And theoretically, if the delta V delta T, if that were to go to 0, of course it can't, but if it were to go to 0, I would have exact solution, right? That's what we mean by an approximation. And that's what happens when we have error that gets associated with these numerical techniques. So that's something you have to be aware of and keep track of when you're doing these solutions. Okay, another problem. You've got flow going into this member, pipe 1 here, pipe 2 here. You've got flow coming out here, you've got flow coming out here, but gee, I don't know what it is that's coming out. What's the fundamental relation that I would use to calculate the flow out?
What goes in?
Sequence balance.
Oh, say again?
Mass balance, or
Yeah, conservation of mass. Right, whatever flows in, got to balance with what flows out. If it doesn't, what's going on? And something would be created inside this. And we're not doing that in this course. All right, so we know that we can balance this by just doing a conservation of mass. All right, what are the governing equations? Simple enough. Flow rate 1, flow rate 2 is equal to flow rate 3 out, flow rate 4 out. So all we have to do is balance it. How do I do that? Remember what Q is? How many of you have had fluids? Some of you didn't have fluids from me. Who'd you have fluids from?
Sheezy. Sheezy Paul.
Dr. Sheezy.
Okay. All right. So you probably recognize this. This is actually coming from what equation? It starts with a B. Bernoulli. All right. So we're saying, okay, here's the flow rate, so it's velocity divided by area, so these things have to balance. So if I know all of these but one, it's easy enough to find. All right. Kind of a trivial solution. Sometimes when you have a lot of these different pipes in, pipes out, then it gets to the point where it becomes very tedious for you to try to do it, you know, with pad and pencil. So put it on the computer. All right, so flow in equal flow out. What's the terminal speed of the bungee jump? How would you calculate that? Okay, so you know that if I'm reaching a steady state condition, then the forces are going to have to balance. So the gravity force, the pull of gravity has to balance the air resistance, right? So what we do is just equate the forces. From that, we can determine what the terminal velocity would be. What I suggest you do is run that for yourself, knowing your mass or weight. You know what G is, just assume some C sub D, something pretty simple, maybe 0.2 or whatever, and you can determine what your terminal velocity is. Generally, for a human, it's about 120 miles an hour. All right, now, there are a number of problems that are somewhat generic in the sense that if you understand how to do one problem, it's not difficult for you to adapt and do a different problem. The only thing that may change are the units, the boundary conditions to the problem. The governing equation may look the same, but it may be a different variable. So, as an example, in chemical engineering, conservation of mass. That's a big thing in that field, obviously. What flows in has to balance what flows out. Here's force balances, basically civil engineering. You remember this from statics, right? So things have to balance out as far as forces. Now what happens when those structures are moving? What's it called? Dynamics, right? When you got things that are moving. Okay. In mechanical engineering, conservation of momentum. Here we're talking about the bungee jump, right? The balance of upward and downward forces. With regard now, the reason this is a second order equation, not a first order, is that the velocity, so I have dv dt, but velocity is equal to what? Distance, right, from time. All right, so I can replace the v, right, by gradient, which now gives me a second derivative. This may be more familiar to you when you had dynamics, where you had x with a double dot over it, or x with a dot, or whatever. It means a derivative, first or second derivative. So here in electrical engineering, how many of you have had double E course? Okay, so you've been through circuits and so forth, so you know about these balances, the conservation of charge, and so forth. The flow of electrons into a node, out of a node, you notice, that's conservation. That's just kind of like these up here. So there's a great deal of similarity. And that's what this course can help you with in looking at problems other than what's just one specific type of situation. So the techniques that we will go over will be relatively generic, and that is that you can use them for a wide range of problems. This is the summary of the methods that we'll actually be discussing throughout the course. The first thing will be roots of equations. And that means basically if I have an equation, I want to find the root. What do we mean by the root? What's the value when it crosses, say, that abscissa or the coordinate, right? What's the zero value? That's what I'm looking for. What's a solution at a particular time or location? This is what you will be doing as far as the first homework that you do, and we'll actually get into that next Tuesday. Now, next Tuesday, I will make the first assignment to you. So here it is, you've got 2 weeks to go. But then what we'll be discussing then over the next couple of weeks is actually solutions. What do we mean by roots of equations and how do we go about solving these things? Also, we will be talking about linear algebraic equations. Basically, what's the solution to these set of linear equations? We tend to do things here in matrices. And so I'm sure you remember somewhere probably about the 6th or 7th grade when you solved your first set of simultaneous equations. You had 3 equations and 3 unknowns, right? You remember what grade you did that in? They didn't dare tell you that it was you're dealing with linear algebra or solving matrices. If they did, every student at that age would jump ship. You know, they'd never do math again. So what they did was subtly bring you into doing these things by hand and solving 3 equations, 3 unknowns. Anybody have to do more than 3? Yeah, okay. Every once in a while, there's a psychopath instructor at that level that says, "Oh, how about doing a 4x4 or 5x5?" And then you suddenly realize how many 3x3s are embedded within those kinds of matrices. So coming up with efficient matrix solvers will be very, very important. And that's really how you want to address these kinds of problems. Optimization, basically determining what is a maximum or minimum. Here, this actually comes back to calculus, and I think you'll remember that. You're talking about first and second derivatives, either greater than 0, less than 0. All right, curve fit. Here you've got some data, and you say, well, what I want to come up with is an expression or a relation that best defines what that data is trying to tell me. And if I want to do some forecasting or some estimates as to what would happen in the future or somewhere down the road, what is it that I need to do? Well, one thing I can do is a regression analysis. Have any of you done least squares? Does that show up? Okay. Probably not yet, but it will. You will be introduced to least squares in this course, so that when you get hit with this in other courses later on, it won't be a surprise to you. Also, interpolation. If I have a number of points here, and I want to put a curve through these points, the issue here is, do I have a curve that actually goes like this, or do I have a curve that I want to fit through every point? Sometimes you want to do that, sometimes you don't, right? So it's going to be a toss-up between something like this or something like this. This is where the use of cubic splines becomes very important to you, because a spline will always fit 3 points. And so you just do 3 points through all the points, and you match them up, and then you have a solution that goes through every point. Obviously, integration. If I want to solve an integral, then I want to do that numerically. There are a number of techniques that we use to do numerical integration. Gauss quadrature is one of those. It's one of the more famous ones. Simpson's rule, all sorts of different techniques. Those are the most popular. For those of you that ultimately wind up doing any finite element analysis, that is an integral technique. And knowing what to do with regard to solving either ordinary or partial differential equations with integral methods will become valuable to you later on, particularly if you're going into finite element and structures analysis. Solving ODEs. A number of techniques that are available for solving ordinary differential equations. Generally, the kinds of problems that we deal with here, you'll have an analytical solution, or you know you can come up with one. And what you want to do is verify or say, gee, how good is the numerical method that I'm using? Some of the more common methods used here are called Brundtland-Kutta methods, that you may have run across that somewhere before, maybe one of the other courses. Somebody mentions that we're solving an ODE here. Our Euler's method, the bungee jumping that I showed you, that was a solution of an ordinary differential equation, right? Then finally, we talk about partial differential equations. Now, in partial differential equations, you will be able to identify the 3 types of equations, either parabolic, hyperbolic, or elliptic. By the way, does anybody know what kind of equation this is? You have one of three guesses. It's either elliptic, hyperbolic, or parabolic. Anybody want to take a guess?
Parabolic. I think this is.
Okay. Who says parabolic? Okay. Well, I got 1.5 votes for that. Who says elliptic? 1, 2, you can't vote twice now. 1, 2, 3, 4. Okay. That means the rest of you assume that it's hyperbolic, right? There's no abstention. And it's always one. Okay? This is a Poisson equation. And a Poisson equation is an elliptic equation. If I set this equal to 0, it's called a Laplace equation. Now, the reason you have to be able to identify the equations is that it dictates the type of numerical method that you will use for this. Now, this says there's no time-dependent term in that equation. Right? So that means that's a steady state equation. So what I have to do is to solve this equation so that the solution converges to a set value. There's a unique solution or set of numbers that will be used for that equation, depending on the boundary conditions. So that means I want to use an iterative technique, or maybe a direct solver that will have this thing converge to that solution. We need to know what that is, okay? And identifying those types of equations. If you get into fluid mechanics, you will find that you're dealing with parabolic and elliptic equations. In fact, you'll be dealing with all three classes of equations. And depending on the equation set, says, oh, I have to use this method, or no, I have to use that method. Generally, if you use the wrong method, you will have a devil of a time trying to get a solution. So it becomes important to you that you now start putting on your mathematics hat a little bit to be able to identify these kinds of equations. Okay, now, for those of you that want to get Maple, the cost is $75. You go to that site, www.maplesoft.com. It will say, okay, you're a student, you're enrolled in this course. This course has been adopted by Maple, and they're going to ask for the promotion code. And so you punch in that code. And then I think you can either download it or they send it to you or whatever. But the cost is $75, which is significantly cheaper than anywhere else if you want that package. It's a very good one. It will ask for the course. The course is MEG 402. Also, notice for those that are using MathCAD, we have bought MathCAD for our students. We plan to distribute it to those who are in classes that use it from Mohammed Trabia. That means you go into the office and you say, I am in 402. We are using MathCAD, and they go, okay, you get a copy of MathCAD. Or you can go out and buy it somewhere if you want for what, $199. Anyway, because you're taking this course, you can get that, or you can get your own copy of Maple for $75. As far as MATLAB, that's already embedded here in the school on PCs and so forth. Okay, so this ends the first week. Now, what I want you to do, review chapters 1 and 2 of the book. All right? And you've got a nice 3-day weekend. I know you don't have anything to do, so this will certainly help you out. Once you get through 1 and 2, start glancing through chapter 4, because this is where we really begin the course. And that's roots of equations. And that's going to be your first assignment. You'll be dealing with roots of equations, interval halving, stuff like that. It shows up in that chapter. Also, begin investigating programming languages, or at least the software kernels that you plan to use. Now, I assume that most of you will be using MATLAB. All right? For those of you that aren't using MATLAB, if you got any questions, come by and see us. Not that we can help you. We might get you in more trouble than anything else. I want to be sure that you notice that Dr. Shalene Wong is here. and she is really a pro in programming languages. So if you get stuck, you really want to track her down. She's on the 3rd floor of the Supercomputer Center, A307. Is that the room? That's if you can't find me. So if I hear you coming, I'll probably hide so that you have to go see Shane. Okay. Any questions?
No.
Okay.
You said that you're posting all these on websites.
Yeah, by the way, I did contact WebCT. They are setting up a site, and they will automatically upload, so they say, automatically upload your name so that you will have access to the slides. On the video that we did on Tuesday, 3.3 gig. So I don't know what happens if you try to run that. This one may be the same, I'm not sure. But anyway, we will try to make them available to you. Certainly, these slides will be available, but we'll try to get the lectures up. Well, I hope so. We're going to try to talk with them and see what they say. Okay.